Today, we're diving into something you've definitely come across, whether you realize it or not. Microcontrollers. These little devices are at the heart of so many everyday gadgets, and today, we'll break down exactly what they are, what they do, and why they're so important. So, let's start with the basics. What is a microcontroller? Simply put, a microcontroller is a small integrated circuit, or IC, that's used to control other parts of an electronic system. Think of it like the brain behind the scenes, managing the flow of information and handling various tasks within a device. When we talk about microcontrollers, you'll often see the abbreviation MCU, which stands for microcontroller unit. Sometimes, you might even see it written as micro C, where the Greek letter mu replaces micro. But no matter how it's written, it's all referring to the same thing. The name microcontroller is actually perfect for what these devices do. The word micro implies that it's small, and controller tells us it's designed to manage or control other parts of a system. And that's exactly what microcontrollers are meant for. They're compact, powerful, and able to quickly respond to signals and control various functions in real time. Alright, now that we know what a microcontroller is, let's dive into how it actually works. It's not just sitting there inside a device, it's working constantly to control specific functions. So, think of a microcontroller as being embedded within a system to manage one particular job. It gets data, processes it, and then acts based on what it's been told to do. Here's a step-by-step look at how it all works. First, the microcontroller receives data from its input-output peripherals, think sensors or buttons, for example. This information is stored temporarily in what's called its data memory. The central processor processes the information, decides what needs to be done, and then uses its output peripherals to send commands that control other parts of the device. To make it even clearer, let's use a car as an example. A modern car has multiple microcontrollers, each managing a specific system. For instance, one microcontroller might handle the anti-lock braking system, another could control the fuel injection to make sure the engine gets the right amount of fuel. There might even be separate microcontrollers for traction control, suspension, and more. Each of these microcontrollers communicates with others to share information and ensure the whole car functions smoothly. So now, let's get into the elements that make up a microcontroller. These are the core components that allow it to function effectively. A microcontroller consists of a central processing unit, or CPU, non-volatile memory, volatile memory, peripherals, and support circuitry. Let's break down each element, starting with the CPU. The CPU, or central processing unit, is essentially the brain of the microcontroller. It performs arithmetic operations, manages the flow of data, and generates control signals. These tasks are all based on a sequence of instructions created by the programmer. Now, you don't actually see the complex circuitry inside the CPU. As a programmer, you typically work with high-level programming languages, like C. Memory in a microcontroller is crucial because it stores the instructions and data the CPU needs to execute tasks. It comes in two main forms. 1. Non-volatile memory. Non-volatile memory is where the microcontroller's program is stored. This program is a series of machine language instructions that tell the CPU what to do. Most microcontrollers use a type of non-volatile memory called flash memory, which retains data even when the device is powered off. 2. Volatile memory, RAM. On the other hand, volatile memory, or RAM, is used for temporary data storage. This data is only needed while the microcontroller is running and is lost when the device loses power. Additionally, the CPU has internal registers that act as temporary storage for data during operations. Now, let's talk about peripherals. Peripherals are additional hardware modules within the microcontroller that allow it to interact with the outside world. They make the microcontroller versatile and capable of working in various environments. Let's go over some of the main categories of peripherals. Data converters. These include analog to digital converters, ADC, digital to analog converters, DAC, and reference voltage generators. They translate signals between analog and digital forms so the microcontroller can process data from the real world. Clock generation. This includes internal oscillators, crystal drive circuitry, and phase-locked loops, PLL. These components provide timing signals that keep the microcontroller operating in sync. Timing peripherals are incredibly useful, like general-purpose timers, real-time clocks, external event counters, and pulse width modulation, PWM, modules. These modules allow precise timing operations, enables measuring time intervals. Analog signal processing. These peripherals include operational amplifiers and analog comparators, which help the microcontroller handle analog signals directly. This can be especially useful in applications involving audio or sensor data. Input, output. This includes general-purpose digital I/O and parallel memory interfaces, allowing the microcontroller to read inputs from other digital components. Serial communication. These peripherals allow the microcontroller to communicate with other digital devices using protocols like UART, SPI, I2C, and USB. This is especially useful for connecting with other controllers, sensors, or external storage devices. In addition to peripherals, microcontrollers also have support circuitry. Debug circuitry. This lets developers monitor the microcontroller as it executes instructions. Debug circuitry. Optimizing code performance, especially in complex programs where bugs may be hard to spot. Interrupts are a powerful feature that helps the microcontroller respond immediately to specific events, either external or internal. This is especially useful in real-time applications where immediate response is critical. Clock generation module. While clock modules can serve as peripherals, their main purpose is often to supply the microcontroller itself with a clock signal. This keeps the CPU and peripherals synchronized and operating efficiently. Internal oscillators are common, and while they may not have the highest precision, they save space and simplify the design. Power supply circuitry. Power circuitry like integrated voltage regulators, power management modules, and supervisor modules ensure stable and efficient operation. They manage power distribution within the microcontroller, help to reduce current consumption during inactive periods. If you enjoyed this breakdown, please hit that like button and subscribe for more tech insights.